Given a function f from a to b and a function g from b to c, define the composition g following f from a to c by gf of x is g of f of x. So we say that as g following f of x. So the picture looks like this. This would be x, and then via the function f, you go to f of x, and then via the function g, f of x goes to g of f of x. But this is also the composition function g following f, so that's g f x. Okay. So we had a couple examples here. We have this function that we've been talking a little bit about, 3x plus 1 over x plus 2, that function from the reals to the reals. Well, the reals minus negative 2 to the reals minus 3. And g from the reals, the entire set of reals, just x squared. And, we talked about the compositions of those functions. And then, this is an important point. No, sorry. Function composed with itself, g following g, that's just written as g squared. But here, this is the point we left off on. Gf is not equal to fg in general. G following f is not equal to f following g. Right, we have the example right here. Basic example right here. Right, like in our examples above, right, g following f is 3x plus 1 over x plus 2 squared, and this is 3x squared plus 1 over x squared plus 2. They're different functions. They're not the same at all. All right. Inverse functions well, given a function f, from D to R, given a bijection, f from D to R, we can define where, f of x is equal to y. We can define a function f inverse from R to D by f of y equals x. That is, f inverse is the function for which f inverse of x equals x, and f inverse f of following f, f inverse of y, f following f inverse of y is always y, and f inverse following f of x is always x. So, for example, let's go back to that Moebius function 3x plus 1 over x plus 2. All right, defines a function f from r minus -2 to the real numbers minus 3. Well, defines a bijection. Now, it has to be a bijection. If you don't have a bijection, there's no inverse function. Okay? You cannot have an inverse function if you don't have a bijection. And problem number 4 on the homework sort of explores that idea a little bit. Not much, but a little bit. So with assignment 3 here on functions, assignment 4 on functions, let f from d to r be a surjective function. So this function is surjective, but it's not going to be injective. And define a function g from r to d, satisfying the property that g of y is in the. So by the way, notice the same notation is used for preimage as it is for inverse function. Right, but preimage isn't a function from range to domain. Right? Inverse functions are functions. Preimage isn't a function from range to domain. Why the same notation? Why do we use the same notation for preimage and inverse function? Why would you use the same notation? Just to confuse you?
I mean, don't they essentially mean the same thing?
Right. I mean, preimage is a generalization of. It's not really a generalization. Yeah, it's a generalization of the idea of an inverse function. Okay, preimage it's a larger idea than inverse function, yet it incorporates the idea of an inverse function. Right? What does generalization mean? So a generalization. Well, let me not get into that. That's a little bit more esoteric than other things we need to study. It's a larger idea that contains the idea of an inverse function. But just because you define your function g to be a member of the preimage, it doesn't mean that g f x is going to be equal to x. Right? And the reason why it fails, right, is not because the function is not surjective, it is surjective. The reason why it fails is because the function is not going to be injective. Right? So you're going to give an example of a non-injective yet surjective function from d to r, for which this fails for some x in the domain. So, when you don't have that injectivity along with surjectivity, you just don't get inverse functions. So, anyway, back to here. This here, we showed that it's injective and we showed it's surjective. So it's a bijection. We showed that already. Okay. Before that f is both injective and surjective. All right, so there should be an inverse function. All right, so f inverse should exist. Well, not should, but does exist. What is it? How can we find it in this case? I mean, not in general for all functions, but but for this particular function, right? Remember, right? F of x is equal to y, and f inverse of y should then be equal to x, and that makes sense because we're injective and surgical, or because we're injective. This one. So basically, right, y equal to 3x plus 1 over x plus 2, and solve for x. Right, so here we're actually doing some algebra. It's not like when you have y is equal to sine x, and therefore x is equal to arc sine y. I mean, here we're just defining the inverse function to be the inverse function, and we're just giving it a name because there's no way to solve algebraically. There's no, there's no way to get an expression for arc sine just immediately from this. But with such a function, actually, you can. Does anybody know what the answer turns out to be? Does anyone know what the answer turns out to be? Does anyone know the punchline ahead of time? Someone must know. Come on. Did anyone take complex variables yet? 3320. Nobody took that? No. Y'all took matrix algebra, right? 3112. What's the inverse matrix of this? It's 1 over the determinant, right? 6 minus 1 is 5. So it's 1/5. How does it go now? I always forget how this goes. 2, 2, right. So it's 2, 3 minus 1 minus 1, right? So that's equal to, let me see, is that right? 6 minus 1 is 5, minus 3 plus 3, 3, or 2 minus 2, and then minus 1, yeah. So this is 2/5 minus 1/5 minus 1/5, 3/5. So I'll just leave that there for the moment. So I mean, y'all know what I'm doing there, right? Inverse matrix. Right. It's going to be this Mobius function corresponding to the inverse matrix. Watch. So y is equal to 3x plus, well, so y times x plus 2 is equal to 3x plus 1. So xy plus 2y equals 3x plus 1. And then, oh, I forget what I'm supposed to do here, actually. Right, all the ones with x's on one side. Xy minus 3x is 1 minus 2y. Factor out the x, y minus 3. What did I do wrong here? So x is equal to minus 2y plus 1 over y minus 3. What did I do? It's supposed to be the inverse matrix, but it's not. What happened? So it's minus 2, 1, 1, minus 3. Um, The determinant of this is 6 minus 1 is 5. Well, that, I'm going to have to think about that some more. I thought it was supposed to be the inverse matrix. Sorry for that. Anyway, it does have something to do with it. I'm just not remembering what it is. So F inverse of x is equal to, or F inverse of x, you can switch back to x if you want, or leave it in terms of y, or whatever you want. So minus 2x plus 1 over x minus 3. So now let's check. Let's check this. So F inverse following F of x, right, that's minus 2, and then this is 3x plus 1 over x plus 2 plus 1 over 3x plus 1 over x plus 2 minus 3. So this is equal to, so what we need to do is multiply the minus 2 here. So we got minus 6x minus 2 over x plus 2 plus x plus 2 over x plus 2 over 3x plus 1 over x plus 2 minus 3 times x plus 2 over x plus 2. So this is equal to minus 5x minus 5x minus 5x, right? Minus 6x plus x, and then minus 2 plus 2 over x plus 2 over, and then this is 3x minus 3x, and then 1 minus 2. So that's minus 3x minus 3x, 1 minus 2, so that's minus 1 over x plus 2, which is equal to, alright, what happened here? What did I do wrong? What did I do wrong here? Y, 3x plus 1, x plus 2, so that's xy plus 2y, minus 2y, minus 3x, y minus 3 over 1 minus 2y, oh, no, minus here. 1 minus 6, so that's minus 5, and so that's x. Right, so that checks out. And then the other way around, f of f inverse of x is equal to, so f of f inverse, so that's 3 times that, minus 2x plus 1 over x minus 3 plus 1 over x plus 2 minus 2x plus 1 over x minus 3 minus 3. So this is equal to minus 6x plus 3 plus x minus 3 over x minus 3. And then this is minus 2x plus 1 minus 3x plus 9. Plus 9? Yeah. Over x minus 3. So this becomes minus 6x, so it's minus 5x over x minus 3 over minus 5x. What happened here? Minus 3x plus 9. Did I put the right? X plus 1 over x plus 2. Oh, x plus 2. How I changed it to x minus 3. How did that happen? This is x plus 2. X plus 2. Alright, let's fix that up. So this is equal to minus 6x plus 3 plus x plus 2 over x plus 2 over minus 2x plus 1 minus 3x minus 6 over x plus 2. So those cancel. And we're left with minus 6x plus x let's see. So it's 3 times minus 2x plus 1 over x minus 3. All right. Yes, this is x minus 3. And then plus 2. This is plus 2. All right, almost there. So this is 2x minus 6. Plus x minus 3 over minus 2x plus 1, and then 2x minus 6 over x minus 3. Over x minus 3 over x minus 3. These cancel, and we're left with minus 6x, that's minus 5x, over, and then this is 0 minus 5, so that's x. Alright, so that checks out. So with algebraically defined functions, if they are bijections, you can often find the inverse functions defined as follows. Okay, just when you have y is equal to f of x, solve for x in whatever way that you can, and then once you've solved for x, that thing there is going to be the inverse function. And then you can check it by doing the composition both ways, and you should just come out with x each time. All right. Let's prove the following. Suppose that f from A to B and g from B to C are both injective functions. Okay. Then the composition G following F is injective. Okay, let's give a proof of that. Now, I can't stress to you guys enough the following. If you don't know the meaning of injective, can't do this. If you know the meaning of injective, not the meaning, sorry, the definition. You need to know the definition of injective and the definition of composition. If you don't know the definitions of both, you can't do it. But if you do know the definitions of both, it takes 2 sentences to prove this. 2 sentences. Okay, you need to know the definitions of everything given. When a definition is given, you need to repeat the definition, write down the definition, give yourself examples of the definition, read the definition again, write down the definition again, give some more examples of the definition, things that are not examples of the definition, but maybe they seem like they might be, but they're not. Everything in mathematics really stems from definitions. You define things a certain way, and then you go from there. All right, so that's step 1. That's step 1, knowing those definitions. Okay, without step 1, steps 2, 3, 4, they just don't follow. This is different than what you learned, throughout grade school and calculus and differential equations, if you've taken that already. Basically, your entire learning of mathematics from kindergarten through 12th grade, and then freshman year, sophomore year perhaps, all of that, the definitions of things, they just keep throwing them at you again and again and again until you sort of internalize them. Right? It just becomes some sort of innate language in your mind, like English is like innate for those people who learn it right away, or who become fluent in it, or who learn it from birth, or who are fluent in it, or whatever other language might be your first language. Okay? This is a different process altogether. You got to learn those definitions. Okay? You got to learn the language, because if you don't know the vocabulary of the language, you can't speak. Not but a few sentences. All right, so, fine. What does it mean for this to be injective? What do we know? We know that F is injective, and we know that G is injective. What does it mean for this to be injective? GF. What do we need to show? What does it mean for GF to be injective? The strict definition, not the sort of more intuitive one. Come on, guys.
Sorry, I was thinking of what you need to do to prove that it's injective, not what does it mean for it to be injective.
Right. So we can prove that it's injective, but we need to know what the objective is that we're looking at. What's the goal that we're looking towards? We need to show that what?
Yeah. It's a one-to-one function both ways.
No,
Every element in the domain goes to a unique element in the range.
Right. That's the intuitive. That's the intuitive definition. What is the strict definition, more so. GF X equals GFY what? If X and Y are different, right, one-to-one functions can't do that, right? When X and Y are different things in the domain, you're not supposed to have that GFX is equal to GFY. So GFX equal to GFY should mean what?
That implies that X equals Y.
Yeah, implies X equals Y. All right, so if GFX equals GFY, then, well, what does GF mean? What does G following F mean?
Take the function f and then plug that answer into the function g.
Right, so what do I write? Yes, yes. So what do I write? How do you write that? G.
G of f of x.
Right. Is equal to G of F of Y. And because,
Implies f of x equals f of y.
right. So Fx equals Fy because what? Why should they be equal?
Because g of x is injective.
Because G is injective. So what now? Fx equals Fy.
X equals y because f is injective.
Exactly. And that's it. You could say as required if you want to be fancy. Right, we started with the notion, with the assumption that g of x, g following f of x, is equal to g following f of y. Now, g following f, by definition of composition, is g of f of x. And this is g of f of y. But g is an injective function, so when g of this is equal to g of that, g is injective. So g of this is equal to g of that, so this is equal to that. All right. So then f of this is equal to f of that, so this is equal to that again. And that's what we wanted to show. Okay, so how about let's try another one. Suppose that f and g are both surjective. That f from A to B and g from B to C are both surjective. Then g following f is surjective. Proof. What do we need to show? G following F, well, let's write the domain and range. Domain is A, range is C, is surjective. So we need to show, well, there's a couple different ways to do that. What does it mean to be surjective? For every element of the range, there's an element of the domain that goes to the range. That for every little c in capital C, there is little a in capital A, such that GF of G following F of A is C. Okay, well, because G is injective, or surjective, because G is surjective, what? What can we do with C because G is surjective?
Could we say that for G of F of A, there is F of C?
Well, C is the range, so we're not gonna.
Okay.
We're not gonna. Let me draw a picture here. We've got this thing C here. It's little c in capital C. And we want to get little a in capital A, such that GF of A is equal to C. Well, what do we know about G? We know that G is surjective. Right, so for every element of the range, for every element in the range of G, there's an element in the domain of G that goes to that range element. So because G is surjective, there is what?
There's an element little b in big B
Yep.
that such that G of B equals C.
Right. Okay. So there's G of B, or there's B here. All right. Well, B is in the range of F, and F is surjective. So what?
So because F is surjective, there is element A in A, such that G or F of A equals B.
There's little a in A, such that F of A is equal to B. So now what? So now, right, C is equal to G of B. B is equal to F of A. So what do I write here?
GF of A.
And G of F of A is what? G of F of A is
C.
I'm sorry, your voice cut off there. What were you saying?
C.
Yeah, it is C, but what is this by definition? What is this expression by definition? It is equal to C. We got that. By definition,
G
expression
following F of A.
G following F of A. The meaning of this is that, right? And this is what we wanted to show. Now we've got it as required. Okay, so when you take compositions of injective functions, you get injective functions. Compositions of surjective functions, you get surjective functions. So compositions of bijections is bijections. So corollary, if F from A to B and G from B to C are bijections, then G following F from A to C is a bijection. So composition of bijections is a bijection. And that's because, it's just something that's both an injection and a surjection. So if these are both injections, so is that. If these are both surjections, so is that. All right, so in the last 10 minutes, what shall we talk about? I didn't think we would be done. Let's look at assignment 4. So in assignment 4, number 1, okay, this is due Wednesday next week, by the way, so a week from today, by 5 o'clock in the Dropbox as usual. So another one of these Mobius function things. So domain is R minus 5, range is R minus 3, and F from D to R is this Mobius function. Prove that F is a bijection. So you have to prove it's injective and surjective. So, we did that for this other Mobius function, right, throughout this section. So, that just follows that. It's just a slightly different function, that's all. Given a function f from D to R, A and B are subsets of the domain. Prove that f of A union B is f of A. The image of A union B is the image of A union the image of B. And then give an example. Sorry, that's a typo there. It says give an example showing that the intersection of the images of A and B is not. Ugh, what did I do? That's all typos. The image of the intersection of A and B is not always equal to the intersection of the images of A and B. I'll rewrite that. I apologize. I didn't realize it was that. Had that there. So anyway, so there's this statement here, and then there's the analogous statement for intersections, right? So this is f of A union B equals f of A union f of B. This should be f of A intersection B is equal to f of A intersection f of B. That's not always true. Okay, and you want to give an example with this domain and this range that shows it's not the case. However, okay, with pre-images, it is true. Okay, pre-image A intersect pre-image B is equal to pre-image A intersection B. So that one you want to prove doing what? How would one prove this? What would be the way to do that? That's the basic strategy. I mean, there are two sets, right? This is a set, and this is a set. All right, so for number 3, so assignment 4, question 3. So to show that preimage A intersection preimage B is equal to preimage A intersection B, okay, show that, here's a template. Use this template. Right, you want to show that preimage A intersection preimage B is what? How do we show that two sets are equal in general? How did we do that? Come on, guys, it was on the exam.
Subset.
Right. Preimage A intersection B. And this part of the proof starts out how? That
Let X be an element of preimage A and preimage B.
mm-hmm. Alright, and then you want to show it's an element of that. Alright, and then the next thing you'd want to show is you want to show that preimage of A intersection B is a subset of preimage A intersection preimage B. So you start with let X be an element of the preimage of A intersection B. And then you go from there to show that F is an element of the preimage of A intersection preimage of B. Okay, please get started on this assignment. Don't leave it till the last day. It ain't gonna happen if you do that. All right. Well, I mean it'll happen, but not in a satisfactory way. If you do that, get started on it today, please. All right. If you guys want to meet with me, email me and let's make an appointment if you're feeling overwhelmed or lost or whatnot. Okay. All right. So I'm here to help, and I want everyone to succeed, and it'll get easier. Trust me. I had a student. She took this class with me 1 year, and then the next year she took Modern Algebra 1 and 2 with me, and she really struggled with the 2800, this class. Didn't do well at all. And then with the Modern Algebra 1, she did a little bit better. But then when we got to the Modern Algebra 2, by the end of the semester, she was all A's. So, I mean, it does sink in eventually. It just takes effort. Okay, so, all right. Have a good afternoon, everybody, and I will see you on Friday.